Hey guys, this is Emil from the LaCoAl₄-type. Today I'll be going over running a density of states calculation, or one of the many different varieties of electronic structure calculations. So I'm just going to log in to my workstation. Perfect. So last time we were working on optimization of one of the demos. So that's the cerium cobalt aluminum 4 type. So we optimized the structure a couple of times. Now to do the density of states, we just go back to the in-car file. Now what we do here is we just comment this part out so it's not read by the system. And then in the template we just do this. And we're working with metals, so ice mirror is going to be set to 1. We're going to have the DOSCAR and PROCAR written. You could and the number of DOS grid points are going to be 1001, and so that gives you a very well enough graph to work with. Now LOrbit actually has a couple of different options. 1 second while I load this up. So the official VASP documentation, you could do a bunch of different things. I know this is a little bit complicated to understand, LM decomposed. I do have a tool for plotting that I'll get into later, but it sort of breaks down after scouring a lot of different forms. It breaks down what each settings do. So 11 to 14, your individual orbitals will be resolved. So that's what they mean by IM decomposed, or might be LM decomposed. Anyways, so you'll get individual orbital contributions from your SP, well not your S, your P and D orbitals if they're available. 0, 1, 2, 5, and 10, your orbitals will be grouped. So you'll have just total P, total D, and of course your S. Now there's other options that you could do that'll adjust sort of your output. Let's see. You could also adjust whether or not you have spin up and spin down. I forgot actually what the input for that was. What is the spin setting? Okay, so in the case of LOrbit equals 10, the RWIGS tag, what is that? That's ignored. This is more complicated than I sort of need, so I'll ignore that in my situation. So I'll just have the density of states, DOSCAR, and the PROCAR file. For plotting, all I need is the DOSCAR. I'm not interested in the individual orbitals or phase factors. These, like I said, are very, are more in depth than I need. Now, how do I spin for density of states? Now, the spin polarized tag, I'm actually not sure what it is, but I guess that's fine because we all learn. So to see I spin, you just add I spin equals 2, and I think that's on the website as well. I'll get into that later, and I'll explain the parsing and everything. Yeah, so if you set I spin equals 2, it'll print your spin up and spin down states for your density of states. So I guess I'll also to LOrbit equals 11 because I want to show the orbital contributions on the plotting graph thing, DOSCAR plotter that I have. Yeah, I think so. That's all I'm gonna go with. I'm gonna ignore the spin because it just tends to complicate things. So for the most part, 10, 11 is fine, and then at least that's what I've just used in the past. And if I'm interested in the spin, I'll just add I spin equals 2. And keep in mind, I am working with VASP 6. Yeah, so that's pretty much it. So I'm gonna keep everything else the same. I know people, they tend to increase their convergence conditions. People also tend to adjust. Oh, also, if you didn't catch that, when I do like a change, I do semicolon WQ and then I'll save it. What was I going into? Oh, so people will tend to increase their mesh, right? So instead of 485, it'll be something more strict, and I'll adjust that, I guess. Actually, I'll keep one the same. I'll rerun in the future, actually. I'm going to leave it 485, but people will tend to increase the mesh. So this is called tightening the mesh. This will be more intensive. Like, it'll take longer to converge, but you'll get more accurate electronic structure. Yeah. So I'll just run this how it is, and if I check the job file, it's running for 12 hours. I'm not sure how long this will take, so I'll do 24, just in case I get problems with running it. Yeah, so that's it. So I'm just going to do sbatch job, and then I will check how it looks. Okay. I'll end the recording here, unless it takes pretty... Okay, maybe I don't have to end the recording here. Yeah, so you can tell the calculations converging because we start off difference in energy at positive 03, and now we're pretty much at the minus 08. So convergence should be coming. Yep. Ooh. High span occupied at some points. Okay. Okay. So I'm gonna get rid of this. I guess I'll just do end band 65, keep that running, and I'll run the job again. Hopefully the error will go away. End bands equals 72. Yeah, I'm not sure what that's about. Actually, running the parallel version of the initialized random numbers, correlated calculations should redo ground state. Alright, fine. For the purpose of this, I'll just ignore it. There we go. Pretty quick conversions. Oh wait. Okay, so now I have the DASCAR and the POSCAR. Those are going to be the only two things that I need. To export those, you do need a particular command. I have it saved somewhere. Okay. So, let's see what I need here. DFT demo underscore CECOAL4. I'm going to put in the downloads as CECOAL4/DASCAR. Okay, so I want the the first, I'm going to get the DASCAR file from this location at this workstation, and I want it installed, copied over locally. So that involves just doing this, and ooh, okay, no such, right, fine, I don't have that folder, so you have to create it. I think there's probably a command where you could just insert if it doesn't exist. I'll do it again, see if it works. Perfect, and I'll do the same with the POSCAR file. Okay, so I get the file from this workstation at this IP address, and I want it saved to downloads, this folder, and saving as, oh, okay, save DASCAR as DASCAR, and save POSCAR as POSCAR in both. Now, I am curious to see if I change the key points. Let's do 8. Actually, before I do that, okay, fine. Yeah, I'll do this to 8, this to 16, and this to 10, and I'll run this all over again. It should technically take longer. Yeah, so it should take longer, but should give us a more accurate electronic structure. Yeah, so it's definitely taking longer. So once you see this at the bottom, it's converged. So now we have two files. We have POSCAR and DASCAR, and we have two folders we're going to work with. Let's say, I'm making the folders in a different screen. So we have CECOAL4, and then I have CECOAL4_type to indicate that it's a tighter mesh. Oh yeah, right. Okay, so same situation as before. Type, and then the same thing with the DASCAR. The only thing that we changed was the K points file in both, but we don't need that because it's not read or used at all. So I do have a I developed software a little bit ago. I recently deployed it as an app. Previously, I mean, I didn't really like the utilization of like different packages because, you know, I'd have to run a Jupyter Lab or Jupyter Notebook. I just felt like there has to be an easier way I could just drag and drop the actual file. So that's what I did. Before that, I was using WX Dragon, and that's very, it's not good. Like, it's very old, very outdated. GUI sort of a mess. I definitely was helpful at a certain point, but it just took me too long to really like extract all the individual XY files, and then I have to, like, if I had to do like The spin orbital, or not spin orbitalized. Um, what's it called? LM, whatever it was. Yeah, if I had to do spin polarized or individual, like, individual orbital resolved options, like it would just be even more of a hassle. So I developed this LaCoAl plotter. So right, I will just literally do this. I compress the file. It's a zip file that has both options, right? Oh, where is this? So I'll take it, and it should get read very. Oh, come on. So I just pushed some updates to make sure that this is supported, and now it works. So the problem was I didn't have support for F orbitals, or I should say compounds with F orbitals. So they have 17 columns. I didn't take that into account. So from here, I'm also going to have to add support for regular compounds with F orbitals, not LM resolved. I think it's local. What is it? Local magnetic quantum number, or something like that, or no, local, whatever it may be. Also spin polarized, and then neither situation. So it works now. So this is exciting. And you could also see the, which one was it? Let's do cerium. Cerium corresponds to which atom? Okay, anyways, I double checked something. So this is perfectly in line with what I see in WX Dragon. So here's the total density of states, and here is, cerium atoms 9 and 10, which correspond to 9 and 10 the POSCAR. So this all works, but I don't have a clunky GUI. I think this works really well. You can also change the axes. They work pretty dynamically as well. So that's all fine and dandy. You can also reset the axes. I have it adjusted from, I think, 2 to pretty deep at the -8 level. You can adjust the position of the Y position of the legend. You can adjust the x-axis limits, and this has a buffer from the max, from the total. Able to toggle the total, toggle every single one, change colors. You also don't need to see the cerium as well, and you could save the plot, and it's pretty high resolution. I tried to have it mimic Matplotlib as much as possible, and I think it works pretty well. You could hide the titles, the scales, whatever you want. So obviously it's not, completely done, but does support a lot. There's a lot of updates I want to include in the future, and they are all found on the All-in Lab website. Just want to make sure everything can be streamlined as much as possible. You don't have to know how to code. In the past, I used Jupyter Lab to do this, and I've just found that, I want to extend it as easily as possible. So yeah, that's pretty much it. So I'll save that. I also have the tighter one that finished up. Yeah, so I guess that actually doesn't do much of a difference. So this is the regular one with the original K points, and this is the, I guess, how do you say it? The tighter mesh. So I'll have them both loaded up. So keep in mind, it does read the folder title, which is why you have this. Anyways, yeah, so not much difference. Oh, I guess the scale is off. Let me adjust that then, so we could compare apples to apples. Wait. Let's see. Yeah, not much difference between the mesh. I guess there are situations in which, you'll pick up on some missed items, so it doesn't hurt. Better be safe than sorry. But yeah, so that's your electronic, or that's your DOSCAR calculation. Very simple, and then streamlines it even more with our own DOSCAR plotter that we developed in the lab. So, like I said, I'll be continuing these with some more electronic structure calculations. Yeah, that's pretty much it. Thank you for watching. Please feel free to leave any comments. Shoot an email if anything comes up. And just know that we will be making sure there's more support in the future. And this is the original GitHub page where we deploy it to Heroku. Anything else in the future, yeah, you could always leave comments here as well, or if you want to contribute as well. So thank you again.